Yeah, so we've basically been doing certain properties of the von Neumann entropy, and you may be wondering where all of this is leading up to, and that's what we'll do starting tomorrow's lecture. We'll actually look at quantum communication or quantum information theory as such, which brings all of whatever we've been doing so far together, right? So why the need to understand von Neumann entropy or even the classical entropy in such detail? Basically because you two don't belong to this class, or you belong to the, huh? Oh, really? Okay. I can speak louder, but you're welcome to sit in the first row. Okay. So what are the things we've done so far already? So we know, of course, so I'm going to write down this definition for a few more lectures. So I'm going to directly write this as this. It is also this. And this, as we discussed, is nothing but the Shannon entropy of the eigenvalue distribution of the density operator, right? So now with this definition, what are the things we've already shown? We've shown that the von Neumann entropy is positive and it is bounded from above by log d to the base 2 for a d-dimensional space, for a d-dimensional quantum system. The second thing we saw was we defined a quantity called the relative entropy, which was useful to show various properties. And we saw that this is a kind of distance measure between states, and the positivity of the relative entropy was a useful tool to prove other interesting properties. Yeah. Oh, I see. That's why I'm not audible, is it? Okay, yeah, please go ahead. Yeah. Is that better? Yeah, they're both density operators on the same space, but like I said, depending on whether the support of rho is contained in the support of sigma or not, this will either blow up or it will be a finite, well-defined quantity, right? So this is trace rho log rho minus rho log sigma, and then when you define it, you will see that rho so this is well defined when the support of rho is contained within the support of sigma. See, normally we assume that these are full rank density matrices on the space, in which case both of them have support on the entire space and there is no issue. But when you're dealing with certain strange, when you have multi-party systems and things have support only on certain subparts, then you have to be careful about how you define this, right? So long as this holds, this definition works, right? Okay. So yeah, we proved the positivity of relative entropy, and using that, we showed subadditivity. Which is basically that if I have a bipartite density matrix, so I have some rho AB, which is a density matrix on HA tensor HB. And as we saw, that this was exactly what we did last lecture. This density matrix, it could either be a pure state, it could be a pure entangled bipartite state, it could be a mixed state but a product state, it could be a mixed but entangled state, right? All possibilities exist. But no matter what the state is, this always holds. So what is the direction of the inequality here? The right hand side is greater. So this is the direction, right? So which are the, so first of all, okay, when is it an equality? If and only if rho AB is exactly the product of the marginals. Okay. So first of all, what is rho A and rho B here? Note that rho A in general is the partial trace. You trace out B, you trace out subsystem B, what remains is rho A. You trace out subsystem A, what remains is rho B, right? Now this need not always be the case. The bipartite need not just be the product of the marginals. In classical probability distributions, this happens when these are independent distributions or independently distributed random variables. In this case, if these two systems are uncorrelated, or these two density matrices are uncorrelated, that is the only case when the density matrix, the bipartite density matrix, factors into this product form, right? Otherwise, it will not in general factor into this product form, and this will be satisfied with strict inequality, right? And the case where you can see that this inequality is really sort of maximal is when this bipartite density operator is a, when is the left hand side 0? Pure. So the left hand side can be 0, but the right hand side can be just log d. There's two reduced states there. It can be 2 log d. So an extreme version of this inequality, we call this an extreme version, is when rho AB is the density operator corresponding to a pure state like this, and this pure state is actually a maximally entangled state of this form. So what I'm writing out now, I'm not sure if I've written this kind of a state before. This would be a maximally entangled state in a d-dimensional Hilbert space. Rather a d cross d dimension Hilbert space. Means HA is a d-dimensional space, HB is a d-dimensional space. We've done simpler examples of this for qubits. We just say I is either 0 or 1, right? And then you get one of the Bell states. So that's an example of a maximally entangled state of 2 qubits. This is a maximally entangled state of 2 qubits, right? And in this case, you can see that the subadditivity basically becomes, the left-hand side is just 0, and the right-hand side can be as large as 2 log d, right? So these are all the limiting cases. There's one case where this is an equality when the entropy of the joint system is the same as the sum of the entropies, but in general, the entropy of the joint system is smaller. In some sense, what it's saying is that your uncertainty about the joint state is lesser than the sum of your uncertainties about the individual systems. And this will be strictly lesser if and only if these two systems are correlated. Just like in the classical case, if you have two probability distributions that are correlated, then your uncertainty about the joint will have to be lesser than the sum of the uncertainty about the individual ones, right? So the same idea here. And I think, defined immediately following this a quantity called the mutual information, right? So a related quantity is the mutual information. So this is the quantum mutual information as opposed to the classical mutual information. And this quantum mutual information is simply the difference in the subadditivity inequality. It's the difference between the sum of the individual entropies and the sum of the joint entropy. Note that I will often use these things interchangeably. So sometimes I'll write SAB and sometimes I write S rho AB. It's understood that these are the same. I hope there's no confusion about that. When I write SA, because after all, these are all specific to some state, right? So we are writing these with reference to some state. So these are all the same. I'll be using this notation interchangeably. Yeah, so and what the subadditivity inequality basically says that this mutual information quantity is always positive. And again, equality if and only if rho AB is a product state. So this mutual information quantity can serve as a measure of entanglement. Because you have a quantity that exactly vanishes if and only if the density matrix is factorizable. So this is what is often called a faithful measure of entanglement, right? It totally vanishes when the bipartite state is a product state. and it is strictly non-zero only when the bipartite state has some correlation or is entangled. There are other desirable properties that measures of entanglement need, and that's a separate theory in itself. It's a whole field of research in itself. Things like monotonicity, things like whether the measure distinguishes between different classes of entanglement, whether it's, now note that this is only a bipartite measure. It's only a measure for bipartite entanglement. Now I can add more quantum systems. Then how do I quantify entanglement? So that's a whole entire field of study. But this is just to tell you that this is already a measure of, let me just say, bipartite entanglement. Okay, so today, so we did one more property where we then saw how does the entropy change under certain quantum operations, right? So the thing that I concluded last lecture with was to say that the von Neumann entropy increases under projective measurements, right? So S of rho will always increase under projective measurements. So you can define a kind of map, right? So this P is, let me say that this is a map associated with measuring some set of projectors, Pi, right? So the set Pi constitutes a set of orthogonal projectors which make up a projective measurement. So in our cartoon box picture, this is what it is. And the outcome is going to be one of these I indices. So I could run from 1 to D. If it's a D-dimensional space, I could have a set of D orthogonal rank 1 projectors, for example. And depending on which outcome is realized, the post-measurement state will be one of Pi rho Pi, right? And so this map, like how we write, a quantum channel or a CPTP map, I can write this as Pi rho Pi, right? So I hope the idea is clear. You're measuring one of a set of orthogonal projectors. And when I say orthogonal, it means Pi Pj is going to be Pi delta Ij, right? Because these are projectors, they square to themselves, right? And so this is the map that you would associate with this measurement, right? An individual outcome is a collapse, but like I always say, you don't, when you think of measurement as a transformation on states or density operators, then you always write down the post-measurement state as if you do not know what the outcome was, right? And that is this form. So what one is saying is, if you go from rho to sum over I Pi rho Pi, now when I write it like this, it should become intuitively clear to you that the entropy has to increase, because this is like a further mixing, right? We've gone from one density matrix. Note that the density matrix itself is a mixture, right? It's a convex mixture of pure states, right? I hope you recall that every density matrix is decomposed as some convex sum of pure states. Now that you're further mixing or randomizing by performing a measurement. So of course, there is one exception when it will not mix this any further, which is that case. Yeah, so we said that that happens when your rho actually commutes with all of the PIs, right? And that will happen. So, okay, so this is the exception. So this is when, okay, let me write down the statement properly and then I will write this. Okay, so under this map, you expect that, so let me call this final state, I think I called it rho prime. Sorry, I will write this condition properly. So the statement is that S of rho prime is greater than or equal to S of rho with equality if and only if rho commutes with all the Pi, which means rho is diagonal in the Pi basis. So associated with a set of orthogonal projectors, you can always write down a basis, right? And the density matrix is diagonal in that basis already. Then, so the pure state version of this would be to say that I'm already in an eigenstate of the observable that you're measuring, right? So if I'm talking pure states, so if this were a transformation like this, and this is what we call a canonical observable, which means it's some Hermitian operator, then it has one of a set of outcomes A1, A2, etc., A sub D. But this measurement transformation will leave the state as a pure state. The state will continue to remain pure after the measurement if and only if this psi was an eigenstate of this observable. Right? So this is just the more general version of this statement. So this is the pure state version of this. Okay, so today let's look at, so this was proved in last class. Today let's look at the next set of properties. So mainly I want to talk about concavity of the entropy today. But since we discussed projective measurement, I want to make two observations. One, I want to say, well, what happens to S of rho under a unitary transformation? And this is something you should be able to tell me. So a unitary transformation is simply rho going to u, rho, u dagger. What happens? Why? Can you prove that? Exactly. So under this, the eigenvalues remain the same. So although I may call this some other sigma, if I write down the spectral form, you can see that the action of this unitary matrix is only to transform one orthonormal basis to another, right? So if rho is sum over I lambda I, then u rho u dagger, which I've called sigma, is simply sum over I lambda I tilde, where I tilde is another orthonormal basis for the space. The unitarity assures us that the transformation from I to I tilde will preserve the norm, will preserve orthogonality. So you end up with, since S of rho is nothing but the Shannon entropy of this eigenvalue distribution, so this is the same as S of sigma. So indeed, the entropy is invariant. So it remains invariant. And this is, I think, a question that someone asked me a while back, whether this has the same interpretation as the entropy in statistical mechanics, which is left invariant under unitary evolution. So indeed, this entropy it is the same entropy that one is talking about, whether you're in statistical physics or in quantum information, right? And it cannot change under unitary evolution. Okay. Yeah, I think I've gotten used to talking to my laptop, so my voice, I'm not even raising my voice, I realize. I hope you can all hear me. Yeah, okay. Yeah. All right, so this was one. So the second thing I want to note, and this I will not really prove or discuss, but I'll give you an example in the tutorial. So I discussed specifically projective measurement, but I did not talk about the larger class of quantum measurements, the POVMs. So it turns out that under a general quantum measurement, for example, the POVM, the entropy can decrease. Okay. So under a general quantum transformation, the entropy can decrease. So one can devise, one can construct artificially CPTP maps under which the entropy can decrease. Okay. So unlike unitary transformations and projections under which the entropy has definite properties, one, it remains invariant, two, it always increases. Under a general transformation, there is no such definite ordering that you can give for the von Neumann entropy. Okay, so we'll look at an example like this in the tutorial. Hopefully, I'll post that in a couple of days. So this was about how the entropy changes under transformations, but now let's actually look at concavity, right? So let's look at, so I want to look at mixtures, entropy of a mixture, and concavity. So what do I mean by mixture? So remember, as we said, rho itself is associated with some convex sum, so let me call this Qi, of pure states. So the physical interpretation of a density operator rho is as if you are picking one of a set of pure states with probability pi, right? Where the state psi I, sorry, here I wrote Qi. So probably state Qi, psi I is picked with probability Qi. But now what if I consider an ensemble of density operators? So this is what I mean by a mixture. I'm now looking at a mixture of density matrices. Okay, and this is the most general scenario that one will actually encounter in a quantum communication setting, and I'll tell you why. So what do I mean by such an ensemble? So it means that I have a set of density operators rho I, each of which is picked with some probability pi. Okay, where will I encounter such a scenario? So you imagine a scenario where I have two parties that are communicating with each other over some quantum channel, right? So tomorrow, this is exactly what we are going to discuss. This is the problem we're going to discuss. This is the general problem of quantum communication, right? Now, what is A going to do? A is going to prepare one of a set of states. Now, you can argue that why should A try to prepare density matrices, which are not really very coherent objects. So A may prepare, for example, a set of pure states, psi I, with probabilities pi to encode whatever information it is that he or she wants to encode and send that across the quantum channel. But see, the quantum channel is a noise map, right? The quantum channel is going to perform a CPTP map on these pure states. So by the time this set of pure states reaches B, it is going to end up looking like this. It's going to end up looking like some ensemble of density matrices. So even though you may argue that it may be beneficial for you to stick to pure states, and often that may not even be the case. For example, you can ask, if I'm given a certain communication channel, is it more optimal for me to encode in pure states or in mixed states? Right? So there may be cases, so we'll hopefully talk about capacity and stuff in the next few lectures, but there may be cases where your capacity is actually reached if you encode in some set of mixed states than in a set of pure states. I'm just saying that it is possible. So I'm just trying to make a case for why you want to consider a mixture of density matrices or an ensemble. So far, we're used to think about ensemble as ensembles of pure states, right? But the most general ensemble that we'll consider from here on will be ensembles of density matrices or mixed states. So one wants to understand how is the entropy of this kind of an ensemble. So the state associated with such an ensemble would be a rho, which is sum over I pi rho I. So I want to understand how is S of rho related to which are the quantities that you can think of here. So you want to know how it is related to S of rho I. You may want to know how it is related to sum over I pi S of rho I, for example. That is the concavity statement, right? The concavity statement says, how is entropy of the convex sum related to the sum of the individual entropies, the convex sum of the individual entropies? So that's the ultimate question that we want to answer, and that will be the concavity property of the von Neumann entropy. But before that, let's look at, okay, so let me state the property. So S of rho is concave, so that's the statement, which implies that, yes, so what will be the relation between these two? What do you expect? It's concave. What you're talking about is convex. So this is the concavity property, that the entropy of the mixture, and again, intuitively, that's what you should expect. You should expect that the entropy of the mixture will be greater than the entropy of the the sum of the entropy of the individual systems, right? Because instead of taking D or whatever number of different density matrices or states, you're actually taking a mixture of these things. So rather than look at them individually, you're now looking at an incoherent mixture of these things. So obviously you will have greater uncertainty about this mixture than about the individual things. So let us look at certain specific cases and then work towards the concavity proof. So let me first talk about what happens when, so let's look at a scenario where, so suppose rho is such that these density matrices rho I that constitute this ensemble have support on orthogonal spaces. Or in other words, they have orthogonal support, right? So what does that mean? It means that trace rho I, rho j will be 0 when I is not equal to j, right? So imagine that I have a set of density matrices which are, loosely speaking, mutually orthogonal. The more formal way of saying it is that they have orthogonal support, right? So in this case, what one can show is that S of rho is actually equal to the Shannon entropy of this distribution Pi. So remember, rho is still this state. It is sum over I Pi rho I plus this. Okay, so let's try to prove this. So of course, the starting point would be to diagonalize each of the density matrices, right? So for each rho I, let me write down a spectral decomposition, which looks like this. So there's a lambda I with a superscript j. And then there is, let me just label this also the same way. Okay. So there's an associated set of eigenstates lambda ij and eigenvalues lambda ij for each ith density operator. Is that clear? J can run from 1 to D. I can be anything. I can run from 1 to n, for example. Okay. The I index tells you which density matrix or which state out of that ensemble you're looking at. The J index tells you which eigenstate of that particular density matrix you're looking at, right? Okay, so now let's write down our usual expression for the Shannon entropy. This is negative trace rho log rho. But you see, rho itself is now of this form, right? So it's Pi rho I. I have written down a spectral decomposition for each of the rho i's. If I now substitute that into the expression for rho, so let me put this here, then what do I get? So then I get a sum over I and a sum over j, Pi lambda ij, ket lambda ij, bra lambda ij. So now obviously the orthogonality property will kick in, but how does that kick in? So I'm going to now say that from this expression, I can read off the Shannon entropy of rho, von Neumann entropy of rho, sorry. Why is that possible? So look at these lambda ij's. So for a given I, lambda ij, lambda ik is 0, right? Because they are eigenstates corresponding to two different eigenvalues of the ith density matrix, right? For a given I, which means for a given rho I, these are two different eigenstates, two distinct eigenstates. And so they are, of course, orthogonal. But across I, since rho I and rho let me say rho L are orthogonal. If I take any lambda ij and any lambda lk, they are also orthogonal, right? It's as if these different rho i's are occupying different parts of my Hilbert space, and in each of them, they are spanned by some lambda ij's, right? Is that idea clear? So this is going to be 0. Okay, so for all I not equal to L and all j not equal to k. Well, actually the j can be the same as the k, it doesn't matter, but for any I not equal to L, this vanishes. And for each, within each I equal to L, it vanishes for every j not equal to k. So let me try to draw a cartoon picture to see, for some of you looking lost. So this is my full space. This is a space that rho I occupies. This is the space that rho L occupies. Now in this space is spanned by some lambda ij kets. This space is spanned by some lambda lk, right? Let me say k going from 1 to something. And this is j going from 1 to something. There is no overlap between these two, right? So this set is mutually orthogonal to this set. And within each set, it's an orthonormal basis. So the bottom line is, what I have in this sum is essentially an orthonormal basis for the complete space. Because I have a set, or if not the complete space, something which can be extended to make an orthonormal basis for the complete space. Because I have a set of mutually orthogonal density matrices. I've taken the spectral decomposition for each of them and I've just put them together. So this itself is a spectral decomposition for rho. Okay? And that's all there is to the proof. Once you recognize that, you simply have to substitute back in S of rho, take a log of the product to be sum of the logs, do the partial sums, and you will get the answer. So why don't you try to do this proof? The key thing is to realize that because these density matrices have orthogonal support, you diagonalize each of them and you write down the full density matrix, then that's it. You have the spectral form. So which are the eigenvalues of this rho now? They are simply pi times lambda ij, right? So S of rho is now minus sum over ij pi lambda ij log pi lambda ij, right? Because the eigenvalues of rho are simply this product. So this becomes two sums. And in the first sum, you can do just the j sum separately. So what would be sum over j lambda ij? That's simply summing over the eigenvalues of density matrix rho I. So that should be 1. So the first term becomes sum over I pi log pi as required. That's the Shannon entropy of the pi distribution. And the second term, I can no longer do this trick, right? But I can take the sum over j inside. Okay. So the second term, let me write it out, is sum over I pi, sum over j lambda I j log lambda ij. So now if you look at this, so this is h of pi plus sum over I pi minus sum over j. So for each I, you're now summing over the j's and you're doing lambda ij log lambda ij. So that's the Shannon entropy for the eigenvalue distribution of the ith density matrix, right? So this becomes So this is the Shannon entropy for the ith. So this is h of lambda ij, where the summation index is over j alone, right? So I'm just putting the index j separately. So this is nothing but, sorry, these are the, remember, eigenvalues of rho I, and you're taking the Shannon entropy of the eigenvalues of rho I. So that will give you the von Neumann entropy of rho I, and that's what you needed to show. Okay. So if you have a set of density matrices which are mutually orthogonal and you make an ensemble of those, then the entropy of the mixture is the entropy of the Shannon entropy of the distribution over which these density matrices are distributed, plus the convex sum of the individual entropies. So from this, you can obviously see that S of rho is always greater than sum over I pi S of rho I, right? With the difference being the Shannon entropy of the PIs. Again, this should make intuitive sense, because what this is saying is, I have a bunch of density matrices, which have support on different parts of the Hilbert space. So there's a rho 1, there's a rho 2, there's a rho 3, there's a rho 4, etc. Now, if I make a mixture of all of this, I have uncertainty coming from two sources. One, from my lack of knowledge about the index I. I don't know which rho I. And the second uncertainty comes from the intrinsic entropy of each of those rows, each of those density matrices, right? So there are two sources of uncertainty. One, so the Shannon entropy of this H of Pi is basically capturing the uncertainty that I have about the index I, about the value of the index I, right? Suppose this Pi was a delta distribution, it means I just have a single density matrix. Then I know what, so then S of rho is simply S of rho, whichever rho that is, and that's it. If this Pi is a uniform distribution, then I'm maximally uncertain about the value of that index I. So that is being captured by the Shannon entropy of that classical distribution. And the second part comes from the intrinsic uncertainty of each of the rho i's that constitute your ensemble. So this is why it makes intuitive sense that the entropy of a mixture should be greater than the convex sum of the individual entropies. And in the special case where this mixture is made up of orthogonal density matrices, that difference is exactly the uncertainty that you have about the index I. Okay, fine. So this is a nice, useful result to know. Keep in mind that this is true if and only if the rho I are mutually orthogonal. Okay, right. So this was one sub case of the concavity proof. The second case that I wanted to do was when this density matrix is now a bipartite density matrix. Okay, so remember that we are working towards showing this finally. Huh? That, yeah, yeah. They have supported on orthogonal. Indeed. So if you look at the proof, it was fully classical. Exactly. Yeah. So this is the classical limit. But now we'll see how we'll use this both to prove concavity, and more generally what will happen is this equality will become an inequality. Okay. And this will actually form an upper bound for S of rho. S of rho is lower bounded by sum over I pi S of rho I. That's the concavity statement. It will turn out that this extreme case where these individual density matrices are orthogonal, which is, as you said, the classical case, is essentially like having a set of classical probability distributions which you mix. And that's exactly what will happen. You have pi qij, right? I just called it lambda ij as eigenstates. That's all. Exactly. So this is a classical limit. It's one limit of this thing. Yeah. Indeed. Okay, so let's now prove a second result, which has to do with a bipartite density matrix. So suppose I have a bipartite density matrix. of this form. So let me write down the density matrix and then I will write down the ensemble that I associate with it. Okay, so the understanding is I have two subsystems. So let me call this as subsystem A and this is subsystem B. Okay, and one is preparing product states of this form. Okay, so let me say that this ket I, which lives in the second subsystem, the HB subsystem. So this is an orthonormal basis for HB. Okay, so I'm preparing product states of this form. Rho I in A, tensor, just the projection onto ket I in B. And then I'm making a convex sum of this form. So this is the ensemble, right? So this is the bipartite ensemble that one is looking at. Again, physically, one scenario where this may happen or where one can understand this is when I'm preparing a set of density matrices. I am a sender, for example, I'm the encoder of a communication protocol. I prepare a set of density matrices according to some distribution, but I want to keep a record of the index associated with each of these. So this I, which is the second system, is often what is called a reference system, which keeps a record of the index I. And this is often called a classical record because I am encoding this index I into one of a set of orthogonal states. Okay. So if you're used to thinking about classical communication protocols, you often talk of a code book, for example. So it may be that the set of density matrices rho I is what constitutes my code words that I have to send. But I want to keep a record of this code book with me, where I know that, or at least I can then say that tell even the receiver that index I means it corresponds to this classical record ket I, right? So this is often an auxiliary system or a reference system with a classical record of which of these density matrices was prepared, right? So what can one say about the entropy of this bipartite state? So it turns out that this is a simple corollary actually of what we just proved, but it's useful to note this, that the entropy of such a bipartite state, which is prepared like this, is nothing but the same thing. So it's the classical, again, it's the same thing, right? You have a classical record of the index, right? And then you have this mixture of states. Okay. So how can one show this? So like I said, it's a simple corollary of whatever we called a property A or whatever, what we just proved above. So what did we show above? We said that if there is a density matrix, which is made, there's an ensemble which is made up of orthogonal states, orthogonal density operators, then this holds. So indeed, that's the case, right? So if I were to think of this rho AB, this is an ensemble of this form. I'll call this sigma I AB, where each sigma I is nothing but rho I tensor projection onto ket I in B, right? And because these ket I's form an orthonormal basis for B, if I now take the inner product or the trace overlap between sigma I and sigma J, then this is 0 for I not equal to J. Right? So essentially, I have a mixture again of density matrices with orthogonal support. And so whatever we discussed above must hold. And so I hope you can now see that. So this is, so they all have orthogonal support. Okay. And so that implies this. Okay. So now with these two properties done, we can actually just prove concavity very easily. So let me do that. So let's actually write down the concavity statement now. So you just need to show that S of rho is always greater than equal to sum over I pi S of rho I. So the way to do this is, now this is a common technique that's often used in quantum information proofs, and this is the first time that we'll be using it. So I'm just trying to make a note of this. What we will do is, now rho itself is a density matrix on some Hilbert space, right? So it's a density operator on some space which we just call H sub A. So I'm going to now extend this Hilbert space, attach an auxiliary system, and I'm going to prepare exactly that kind of state where each of these density matrices rho I comes attached with a reference index in that auxiliary system. And then I'm going to use subadditivity for this bipartite system, and that statement will reduce to concavity for the one of the reduced subsystems. Okay, so when I state concavity, I should also say when equality holds, right? So when does equality hold in a regular? Is there a class here? Sorry, are they all peeping in? Like, I don't know. Can they understand by staring at this from outside? I'm not sure. Okay, yeah. So when would this hold with equality? It's like any other convex function or concave function. Exactly. So there are two cases in which this can happen. Either Pi is a delta distribution. So there's only one density matrix that is picked, or all the rho I are the same. So in both cases, you have only one term in the sum, right? And that's the case when concavity is usually saturated. So there's only one term in the sum. When you make the convex sum. So this can happen in one of two ways. Either these density matrices are all the same, or that there is an ensemble, but you're picking this according to a delta distribution, right? Okay, so the proof of this, like I said, you start with rho being a density operator on some Hilbert space. Now we construct a bipartite state. So what has been given to us is that rho is a convex mixture like this, right? So this is what is given to you, right? So construct a bipartite state, and let me call this something else, maybe sigma AB, where again you pick each of these density matrices rho I according to the same probability distribution Pi, but then you attach what I call the classical record of this in subsystem B, okay, where this is important. This is an orthonormal basis for B. So you pick another Hilbert space which is isomorphic to HA, which is the same dimension as HA, and then you construct a bipartite state on this. So now I want you to tell me what are the marginal density matrices. So what is the, if I trace out B, what do I get? And if I trace out A, what do I get? So can you work this out for me? Let me just find out if they have a class. Anyway, let's complete this and then we'll continue tomorrow. We'll take a. So rho means it's going to be sum over I pi rho I, correct? Yes. So this is indeed rho. So you see, this is the advantage of doing this bipartite extension, that you have made sure that one of the reduced density matrices is the state itself that you want to, whose concavity, I mean, whose property you want to analyze. And what about sigma b? Yes, but what is it? Work it out. Remember that each rho I is a density matrix, which means its trace is 1 on subsystem A. So yes, identity. Yeah, so it's going to be sum over I, pi, I. Hi, Prem. Yeah, I teach here till 3:15 usually, but it's okay. I'll just wrap up. Just give me a minute. I will just wrap up, Prem. Sorry. Yeah. Just give me a minute. Okay. So you've reached this far. Now all that remains is for you to do subadditivity. So I'm going to just leave you with this. Tomorrow we'll complete this proof if you are not able to do it. So now use subadditivity, which means S of this, for which state? For this bipartite state. So S of sigma AB is less than equal to S of A plus S of B, or S of sigma A plus S of sigma B. So the claim is that this is exactly the same as saying that S of sum over I pi S of rho I will be less than or equal to S of rho. Okay, so I leave this to you to do as homework, but we can just continue from here tomorrow. Okay, so let us stop here today. I might extend tomorrow's class by 10 minutes so that we make up for this. Okay.